Imagine looking up at the night sky. It looks peaceful, predictable, a quiet tapestry of stars. But that stillness is an illusion. We live in a cosmic shooting gallery. Right now, as you watch this, astronomers are tracking over 34,200 near-Earth objects. Of those, nearly 2,400 are massive enough to survive atmospheric entry and reshape the map of our world. We have been hit before. In 1908, a 65-meter space rock exploded over Tunguska, Siberia, flattening over 2,000 square kilometers of forest with the energy of 440 kilotons of TNT. In 2013, a 20-meter meteor detonated over Chelyabinsk, Russia, shattering glass across 200 square miles and injuring over 1,600 people. These events proved that the threat is not theoretical. It is a historical fact. So, we watch the sky. NASA's Sentry and ESA's Aegis systems continuously calculate impact probabilities. Observatories like the Asteroid Terrestrial Impact Last Alert System, or ATLAS, scan the dark void every 24 hours. The upcoming NEO Surveyor telescope aims to find 90% of the largest threats. We calculate orbits, run simulations, and build a sense of security, but our planetary defense grid has profound blind spots. We are essentially looking through a keyhole. Objects approaching from the direction of the sun can hide in its blinding glare, invisible to our ground-based telescopes until they are almost upon us. Small but devastating rocks under 50 meters routinely slip through our detection thresholds. And then there are the long-period comets, plunging in from the deepest, darkest edges of the outer solar system. For these icy ghosts, our warning time wouldn't be measured in decades, but perhaps in mere months. The chilling reality is that our safety relies on a fragile mosaic of funding, international coordination, and the assumption that we will see the threat coming with plenty of time to react. In hypothetical planetary defense exercises, simulations often reveal our vulnerabilities. A warning of just a few months leaves us entirely defenseless. Our deep space infrastructure requires years of preparation to launch a countermeasure. We have built models and warning networks, but what happens when the warning comes too late? What happens when the telescopes spot the rock, calculate the trajectory, and the numbers return an absolute certainty of impact? The question is no longer just a thought experiment for scientists. It is the ultimate test of human survival. What if we fail to stop the asteroid? Welcome to Only Cosmic. Let's assume we see it coming. How do we stop a mountain of rock hurtling through space? In 2022, NASA's DART mission proved that we can fight back. By crashing a spacecraft into the 160-meter asteroid Dimorphos at 14,000 miles per hour, scientists successfully shortened its orbit by 32 minutes. It was a triumph of engineering, proving that kinetic impactors work. But the universe does not always provide us with a simple target. Asteroids are not always solid, monolithic blocks of stone. Many are what scientists call rubble piles or contact binaries, loose collections of rock and debris held together by incredibly weak gravity. If you hit a rubble pile with a kinetic impactor, you might not push it off course. Instead, you might shatter it. The single predictable threat suddenly becomes a shotgun blast of multiple unpredictable fragments raining down on Earth. Furthermore, deflecting an asteroid requires an extraordinary level of precision. If we apply slightly less force than calculated, if our models misjudge the asteroid's density or momentum transfer, we trigger the billiard shot effect. Instead of missing Earth entirely, the asteroid is merely pushed into a different trajectory, moving the impact zone from an uninhabited ocean to a densely populated metropolis. A partial failure could trigger an unprecedented geopolitical crisis, shifting the burden of destruction from one nation to another. Scientists have devised alternative methods. The gravity tractor uses a spacecraft's mass to gently pull the asteroid over decades. The Yarkovsky effect involves painting the asteroid to let solar radiation slowly shift its path. The enhanced kinetic impactor concept proposes capturing a smaller asteroid and using it as a battering ram against the primary threat. But all these methods require time. Time we might not have. If the warning is short or the asteroid is massive, science points to a controversial last resort: nuclear deflection. Sandia National Laboratories has demonstrated that a nuclear X-ray pulse, detonated just above the asteroid's surface, could vaporize a layer of rock, creating a massive thrust that pushes the object off course. CERN's High-Radmat facility has tested iron asteroid materials with high-energy proton beams, discovering that iron-rich space rocks can absorb tremendous amounts of energy without breaking apart. Yet, the Outer Space Treaty strictly bans nuclear weapons in space. The ultimate solution to saving our planet is currently locked behind a wall of international law. If bureaucracy delays action and our kinetic attempts shatter or merely nudge the rock, humanity will face the inevitable. The deflection has failed, the asteroid has crossed the threshold, and the sky begins to burn. When we picture an asteroid impact, we often imagine a massive crater, but advanced simulations like those from Imperial College London reveal that the crater is not the primary danger. The true killers are the aerothermal effects, the violent reactions of the atmosphere itself. As the asteroid plunges through the air at supersonic speeds, it violently compresses the atmosphere in front of it. This generates an incomprehensible shockwave. An extreme overpressure wave blasts outward, followed instantly by a rapid drop in pressure. This shockwave is powerful enough to shatter concrete, crush vehicles, and instantly level entire cities. Following this wave are supersonic wind blasts that can uproot vast forests and toss debris for kilometers. Simulations show that for asteroids between 15 and 400 meters, over 60% of all casualties would be caused by these terrifying wind and pressure waves alone. Simultaneously, the kinetic energy of the impact vaporizes the asteroid and the target rock, converting them into a massive fireball. This plasma cloud can reach temperatures exceeding 10,000 Kelvin, hotter than the surface of the Sun. It emits a blinding, lethal thermal radiation that incinerates everything in its line of sight, triggering massive, continent-spanning firestorms. Fortunately, the curvature of the Earth limits this direct thermal devastation, meaning the fire does not wrap around the globe entirely. You might hope the asteroid lands in the ocean. Earth is mostly water after all. But the mega tsunami scenario is deeply misunderstood. An ocean impact creates a massive temporary crater in the water, generating towering rim and collapse waves. Yet, as these immense waves approach the continental shelves, the shallowing water forces them to break and lose much of their energy. The continental shelf acts as a natural dampener. Because of this, striking land is actually an order of magnitude more lethal than striking deep water. But the immediate devastation is only the prelude. If a Bennu-sized asteroid, roughly 500 meters across, strikes the Earth, the real nightmare begins in the stratosphere. The impact forcefully ejects up to 400 million tons of pulverized dust, soot from the firestorms, and, depending on the target rock, massive amounts of sulfur. This toxic cocktail spreads across the globe, wrapping the Earth in a shroud of darkness. The immediate blast may destroy a region, but the dust will transform the entire world, ushering in the true catastrophe. The impact winter. The sky turns black and the Earth begins to freeze. The sheer volume of soot and sulfate aerosols injected into the stratosphere acts as a planetary shield, reflecting the sun's light back into space. Global average temperatures plunge by 4 degrees Celsius. In some regions, the drop is far more severe. Rainfall decreases by 15%. For years, the world experiences an unnatural, freezing twilight. The lack of sunlight triggers a catastrophic biological cascade. Photosynthesis stops. Without the sun, the foundation of the food web collapses. Plant life withers, followed by the herbivores and eventually the predators. We saw this 66 million years ago with the Chicxulub impact. The highly specialized dinosaurs starved, while small mammals and creatures that fed on dead organic matter, detritus, managed to survive. In the oceans, a strange paradox occurs, known as the ocean rebound. While land vegetation dies, the iron-rich dust settling over iron-depleted oceans acts as a massive fertilizer. This triggers an explosive bloom of diatoms and phytoplankton, offering a rare biological lifeline in an otherwise dying biosphere. But on land, the darkness brings another invisible threat. The intense heat of the impact creates nitric oxides, which ravage the ozone layer, causing up to a 70% depletion. When the dust finally settles and the sky clears, the Earth is bombarded by lethal levels of ultraviolet radiation. For human civilization, the crisis is immediate. Modern society relies on hyper-connected, just-in-time supply chains. An impact from a 100-meter asteroid could destroy critical power grids and logistical hubs, causing a global economic collapse. Even a 1-meter meteor, detonating with a bright flash in the atmosphere, could be misidentified by early warning radars as a nuclear missile, potentially triggering an accidental nuclear war. To survive the impact winter, humanity cannot rely on traditional farming. We would have to pivot entirely to resilient foods. This means cultivating fungi that feed on dead timber, farming cellulose-digesting insects, and utilizing methane-consuming bacteria to generate protein without sunlight. Our survival would depend not on the technology that builds rockets, but on our ability to adapt to a world without the sun. An asteroid impact is not just a physical event. It is the ultimate test of our resilience. We look up at the stars not with fear, but with a profound understanding of our fragile place in the cosmos. Thank you for exploring the unknown with us. See you next time on Only Cosmic.